Welcome to Fun Facts Online. Today we're journeying millions of miles across the solar system to the Red Planet. For decades, humanity has been obsessed with Mars. And to unlock its secrets, we've developed a brilliant strategy, sending robots in pairs. This is the story of dual probe missions, a tale of incredible technological triumphs, heartbreaking failures, and the relentless quest to understand our planetary neighbor. So, why send two spacecraft to Mars at the same time? Why not just send one? The answer is all about synergy. The core idea is that two probes working together can achieve far more than two probes working alone. Think of it as having a scout in the sky and a geologist on the ground. The first part of the pair is usually an orbiter. From its high vantage point, the orbiter gets the big picture. It maps the entire planet, studies the atmosphere like a global weather satellite, and scans the surface to identify the most scientifically interesting places to visit. It can spot ancient riverbeds, massive volcanoes, and deep canyons, creating a planetary roadmap for exploration. But an orbiter can only see so much. To really understand what's going on, you need to get up close. That's the job of the second probe, the lander or rover. This surface explorer provides what scientists call ground truth. It's the difference between looking at a picture of a beach and actually feeling the sand and water yourself. A rover can drill into rocks, analyze the chemical makeup of the soil, and search for the complex molecules that might be signs of past life. When you combine the orbiter's global map with the rover's detailed local analysis, you get a powerful, scientific one-two punch. The orbiter might spot a channel that looks like it was carved by water, and mission control can then direct the rover to that exact spot to analyze the sediment and confirm it. Beyond the science, this partnership solves a massive logistical problem: communication. Mars is incredibly far away, and a small rover on the surface, with a limited power supply, would struggle to send large amounts of high-resolution images and data directly back to Earth. It would be like trying to shout across an ocean. The orbiter acts as a crucial communications relay. With its large, powerful antenna always pointed at Earth, it can receive a torrent of data from the surface probe and then blast it back to mission control at a much higher speed. This data relay is the lifeline for every modern Mars rover. Finally, sending two probes offers a degree of insurance. Space exploration is famously risky. A dual mission provides a backup. If the lander tragically fails during its perilous descent, the orbiter can still conduct its own valuable science mission from orbit, ensuring the entire project isn't a total loss. This strategy wasn't invented overnight. It was born from decades of trial and error, starting with the ambitious efforts of the Soviet Union. In the 1960s and 70s, the Soviets were pioneers, launching their Mars program, the first to attempt a dual-probe strategy. In 1971, they launched the identical Mars 2 and Mars 3 spacecraft. Each consisted of an orbiter and a lander. But they had incredibly bad luck. They arrived at the Red Planet during one of the largest, most violent, planet-encircling dust storms ever recorded. The landing sequences were automated and couldn't be changed. The Mars 2 lander entered the atmosphere too steeply, its systems failed, and it crashed. It did, however, earn the title of the first human-made object to touch the surface of Mars. A few days later, Mars 3 fared slightly better. It successfully performed the first ever soft landing on another planet. It was a monumental achievement. For about 20 seconds, after transmitting a single, partial, featureless image, it went silent forever, likely a victim of the ferocious dust storm. Despite the lander failures, the orbiters continued to work for months, sending back images and data, proving that the dual-probe concept had merit, even when part of it failed. The Soviets tried again in 1988 with the Phobos 1 and Phobos 2 missions, designed to study Mars and its mysterious moon, Phobos. Tragically, both were lost. Phobos 1 was lost on its way to Mars due to one of the most infamous typos in history, An engineer uploaded a command sequence containing a single wrong character, a missing hyphen, which caused the spacecraft to lose its lock on the Sun, draining its batteries. Phobos 2 actually made it to Mars orbit and sent back 37 images of its target moon, but just before deploying its landers, contact was lost, likely due to an onboard computer failure. These early missions, though often ending in heartbreak, taught invaluable lessons about the unforgiving nature of interplanetary travel. These lessons paved the way for one of the greatest triumphs in planetary exploration, NASA's Viking program. Launched in 1975, the program consisted of two identical spacecraft, Viking 1 and Viking 2, each with a powerful orbiter and a sophisticated lander. The Viking orbiters were workhorses. They mapped 97% of the Martian surface in stunning detail, revealing towering volcanoes and the vast Valles Marineris Canyon system. They acted as the perfect scouts, surveying safe and interesting landing sites for their partners on the ground. And once the landers were down, the orbiters became their essential communication relay. The Viking landers were technological marvels, each a self-contained robotic laboratory. Their primary mission was profound: to search for life. They carried a robotic arm to scoop up soil, cameras to give us our first panoramic views from the surface, a weather station, a seismometer to detect Marsquakes, and two key instruments for the search for life. The first was a gas chromatograph mass spectrometer, or GCMS, to analyze soil for organic molecules, the building blocks of life as we know it. The second was a dedicated biology experiment with 3 different tests designed to detect signs of metabolism in the soil. The landings themselves were a nail-biting, perfectly choreographed ballet. The landers separated from the orbiters, slammed into the atmosphere protected by a heat shield, deployed parachutes, and then fired retro-rockets for a gentle touchdown. Both landings were flawless. The Viking missions were a spectacular success. The landers operated for years, sending back over 400-500 images and a treasure trove of data. The weather stations recorded the daily temperature swings, and the chemical analysis showed the Martian soil to be an iron-rich clay. But the search for life yielded a deep and enduring mystery. The biology experiments returned positive results, suggesting some kind of chemical activity was happening in the soil. It was an electrifying moment. However, the other instrument, the GCMS, found absolutely no trace of organic molecules. This was a puzzle. How could there be signs of biological activity, but no biological building blocks? This contradiction sparked a debate that continues today. The leading theory is that the Martian soil contains highly reactive chemical compounds, like perchlorates, that mimicked biological activity in the experiments, while simultaneously destroying any organic molecules that might have been present. While Viking didn't find definitive proof of life, it completely transformed our view of Mars, showing us a planet that was once much wetter and more dynamic. It remains the ultimate example of the dual probe strategy executed to perfection. More recently, the European Space Agency, or ESA, has taken up the mantle with its ExoMars program. The first mission, launched in 2016, was another classic dual probe setup: the Trace Gas Orbiter, or TGO, and a lander named Schiaparelli. The TGO is a masterpiece of atmospheric science. Its main job is to hunt for trace gases, especially methane. Methane on Mars is a huge deal because it breaks down quickly in sunlight, so if we detect it, something must be actively producing it. That something could be a geological process, like underground volcanic activity, or, tantalizingly, it could be microbial life. The TGO is currently mapping methane with incredible precision, and it also serves as a vital communication relay for NASA's rovers on the surface. The Schiaparelli lander, however, had a different goal. It was a technology demonstrator, designed purely to test Europe's ability to land on Mars. Unfortunately, it failed. A sensor glitch made the lander's computer think it was much closer to the ground than it actually was. It released its parachute too early, fired its thrusters for only a few seconds, and then plummeted to the surface. But even in this failure, there was a form of success. The lander transmitted data during its entire descent, giving engineers a clear picture of what went wrong. It was a harsh lesson, but a valuable one that will be used to design a safer landing system for the future. The second part of the ExoMars program is the Rosalind Franklin rover. This rover is a life hunter, and its most important tool is a drill capable of reaching 2 meters below the surface. This is a game changer. The Martian surface is bombarded with harsh radiation that would destroy delicate organic molecules. But 2 meters down, those molecules might be preserved. The rover's future is currently uncertain due to a suspension of cooperation with the Russian Space Agency, which was providing the lander. Still, the technology represents a critical next step in the search for life. The dual probe strategy is far from over. NASA's upcoming ESCAPADE mission will use 2 identical, low-cost orbiters, nicknamed Blue and Gold. They will fly in formation, creating a unique stereo view of the Martian atmosphere. This will allow scientists to see, in 3 dimensions, how the solar wind strips away atmospheric gases, helping us understand how Mars lost its once thicker atmosphere and turned into the cold desert it is today. And then there's the most ambitious mission yet, the Mars Sample Return Campaign. This isn't just a dual-probe mission, it's a multi-probe relay race. It's already started with the Perseverance rover, which is collecting and storing promising rock samples. In the future, a second spacecraft, a lander, will arrive to pick up these samples. A small rocket on that lander will then launch the sample container into Mars orbit. Finally, a third spacecraft, an orbiter, will have to rendezvous with and capture that container in orbit and fly it all the way back to Earth. It's an incredibly complex chain of events, the pinnacle of the multi-probe strategy. Looking back, the history of dual-probe missions teaches us that failure is a part of exploration. Every crash, every software bug, every sensor glitch has provided critical data. The lessons from Mars 3, Phobos 1, and Schiaparelli directly contributed to the knowledge that makes missions like Viking, Perseverance, and the future Mars sample return possible. This elegant dance of 2 probes, an eye in the sky and a laboratory on the ground, has fundamentally shaped our understanding of the red planet. It's a strategy built on synergy, communication, and resilience. As we continue to push the boundaries of robotic exploration and look toward the day humans finally walk on Martian soil, we stand on the shoulders of these robotic duos, the pioneers that turned a distant red light in the sky into a world we can explore.